So calorimetry and the application of Hess's law have made available a great many delta H values for chemical reactions. We've been looking at chemical reactions. The table in the back of the book, an appendix, for example, lists standard molar enthalpies of formation. The standard molar enthalpy of formation is the enthalpy change for the formation of 1 mole of a compound directly from its elements in their standard states. So let's look at a few examples of what this looks like. If I wanted to look at the enthalpy of formation, notice that it's denoted as HF for sodium chloride. So I want 1 mole of NaCl. So that means I need to have NaCl is made up of sodium, Na, and Cl, Cl2 actually, because it's diatomic when it's by itself. But I only want 1 mole of NaCl, so therefore I need to have half of a Cl2 plus Na. And so then I can look in the back of the book and it tells me that the heat of formation of NaCl is negative 411.12. Again, note the fraction is required because chlorine gas in its standard state is diatomic, Cl2. We could look at the heat of formation for NaCl that's in aqueous form. And so it's going to be the same equation, it's just going to be aqueous, and we would see that the heat of formation of that is negative 407 as opposed to negative 411. So the heat of formation of solid sodium chloride is more exothermic than aqueous sodium chloride. I mean, not by much, but it is by, about 4 kilojoules. We can also look to see the heat of formation of ethanol at 25 degrees. So we would look at what is made up of C2H5OH. Well, the elements that make it up are carbon, and in its natural standard state, carbon is a solid. Hydrogen also makes it up, and remember that's diatomic, so H2, and oxygen, and that's also diatomic, so it's O2. Now, we only want 1 mole of C2H5OH, so we need to go, okay, well, that takes 2 moles of carbon. We need 6 hydrogens, so 3 moles of diatomic hydrogens. And there's only 1 oxygen, so we only need half of a mole of O2. Now, if you flip to the back of the book or whatever appendix you're using to look at different delta H or enthalpies of formation for different compounds here, notice that the standard enthalpy of formation for an element, so if I just looked at oxygen in its standard state, so O2 is 0. Carbon in its standard state, which is solid in graphite form, is 0. Now carbon as a gas is not standard state, so yes, there is enthalpy of formation for that. Carbon is a diamond. It takes a lot of pressure to make carbon from graphite go to carbon to a diamond. So carbon as a diamond is not in its standard state, so it is not 0. But elements in a standard state are 0. Most delta H values are negative, indicating that forming most compounds from the elements is exothermic. Very few values are positive, and those represent compounds that are pretty unstable with respect to decomposition to the elements. So these couple that are positive are pretty unstable. And so we just covered this one, that elements are 0, most are negative. And the values of these heats of formation can be used to compare thermal stabilities of related compounds and see, which is more stable. Obviously, the exothermic, the negative 273 is more stable than HI, hydroiodic acid, which is positive 25, so that's less stable. Let's do a couple examples. We just did letter A, but how about you try to write letter B? Oh, we did A and F actually. So why don't you try letter B? Write the thermochemical equation representing the standard enthalpy of formation for glucose, C6H12O6. So why don't you pause and try to do that one? And also, why don't you try to do letter C? We'll do B and C together. If I'm trying to create, we're looking at B first. I'm going to have carbon in its standard state is just solid carbon. We know hydrogen in standard state is diatomic, and that's a gas. And oxygen in its standard state is O2 as a gas. And we want 1 mole of C6H12O6. All right, so I need 6 carbons. I need 12 H's, and I need 6 O's. There we go. And we would just need to look up in our appendix to see what C6H12O6 enthalpy of formation is. The second thermochemical equation we'll write, letter C, calcium carbonate. So calcium in a standard state is solid, plus carbon in a standard state is solid, plus oxygen is O2 gas to create CaCO3. So I need 1 calcium, 1 carbon, and 3 oxygens. So to get 3 oxygens from 2 oxygens, 3 halves, right? 3 times 2 is 6 divided by 2 is 3. There we go. So again, we were forming 1 mole, oh, that's a sloppy one, 1 mole of calcium carbonate. So moving on, we can also calculate enthalpy change for a reaction by using the standard molar enthalpies of formation and this equation. So to find the enthalpy of the whole reaction, we can take the sum of our enthalpies for our products of the formation minus the sum of the enthalpies of the formation of the reactants. Now we do have to take into consideration moles. Okay, now we're going to do an example here. So the sum of, we need to take the number of moles times the heat of formation. So multiply heats of formation of products by the number of moles, add them up, and then minus the sum of the formations of products as they're multiplied by the number of moles. And we'll make more sense out of that in this next problem. So here we have calcium carbonate decomposing into calcium oxide and carbon dioxide. So if we look up in the back of the book and the appendix to find the heat of formation or the enthalpy of formation for each of these compounds, it tells us that calcium carbonates, calcium oxide, carbon dioxide, these are all the enthalpy of formations for these 3 compounds. So all we need to do is to sum up the products. Here's our products. So calcium oxide, there's only 1 mole of it, so I'm going to take my calcium oxide, which is negative 635.1, plus my carbon dioxide, which is negative 393.5. So here's my products, and there's only 1 mole of each of those, so I'm multiplying these by 1. Products minus reactants. My reactant is just my calcium carbonate, which is negative 1207.6. And if I plug this into my calculator, let's do negative 635.1 plus negative 393.5. And then I'm getting negative 1028.6. I'm going to minus a negative 1207.6. And I get my heat of the reaction of plus 179 kilojoules. Simply by just taking the sum of my products minus the sum of my reactants. Let's do another one. Let's look at another example problem similar to the last one. This just adds one extra step. So we have nitroglycerin, which is a powerful explosive that forms 4 different gases when detonated. So here's our nitroglycerin. It forms nitrogen, oxygen, carbon dioxide, and water. We want to calculate the enthalpy change that occurs when 10 grams of nitroglycerin is detonated. Okay, so we're going to get to that in a minute. The standard enthalpy of formation nitroglycerin is negative 364. So I'm going to write that right here, negative 364 kilojoules per mole. Use the appendix to find the other values. Well, all right, we know that single lone elements in natural state, so this nitrogen we know is 0, right? 0, heat of formation for nitrogen and for oxygen, 0. But we can look at the back of the book and see that CO2 enthalpy of formation is negative 393.5. And for H2O gas, H2O is negative 241.8. So let's find our delta H for the reaction, our delta HF. So we need to do products minus reactants. So I've got my products, 6 moles of negative 393.5 plus 5 moles of negative 241.8. That's my products minus reactants. I have 2 moles of negative 364. Let's do this here. 6 times negative 393.5 plus 5 times negative 241.8. And then I'm going to minus, put parentheses, 2 times negative 364. All right, so I got delta H this whole chemical reaction of negative 2842 kilojoules per mole. Again, if I go back and look what I just did, I was given delta H, the standard enthalpy of formation for my nitroglycerin. I know that my elements are always 0. For CO2 and H2O, we were given those, or we could have looked them up in the appendix. And then I did products. I remember I had to take those numbers and times it by how many moles there are of it. So there was 6 moles of carbon dioxide, 5 moles of water, minus reactants. There was 2 moles of the nitroglycerin. So products minus reactants to get my delta H for the whole reaction. That should be RXM, reaction. Now, I want to know the enthalpy change that occurs when I have 10 grams of nitroglycerin. So hopefully you're at the point now where you go, oh, 10 grams. I need to get grams to moles. Okay, so we're told nitroglycerin is C3H5, parenthesis, NO33. This is our nitroglycerin. So grams, we need to find the molar mass of this, of 3 carbons, 5 H's, 3 N's, and 9 O's. And if we add it all up, we should get molar mass of 227.1 grams of nitroglycerin. I'm just going to write nitro G, for 1 mole of that. And 10 times 1 divided by 227.1 should give us 0.04403 moles of nitro G glycerin. I'm just abbreviating for the sake of time here. Now, to find, here we go, the enthalpy change that occurs when I have 10 grams of nitroglycerin. So I'm going to start with my moles, 0.04403 moles of nitroglycerin. I know that there's 2 moles of nitroglycerin in this whole reaction. 2 moles of nitroglycerin. There we go. And I know that in this reaction, there's 2 moles of nitroglycerin reacting, and that my delta H for that reaction is negative 2842 kilojoules. So I can use that delta H that I found from my products minus reactants. I went from grams to moles, and I just went, oh, for 2 moles of nitroglycerin, this much energy is released. So now I have my last part is 0.04403 times negative 2842. And I should get, oh, and divided by 2. Negative 62.6 kilojoules is my enthalpy change when I have 10 grams of nitroglycerin reacting. All right, let's do one more here. The combustion of benzene. The question wants us to calculate the standard enthalpy of combustion for benzene. And we're given the equation here. We've got benzene plus oxygen. That's a combustion reaction to give us CO2 and H2O. And we're given that the enthalpy of formation of benzene is plus 49 kilojoules per mole. And then I looked in the appendix to find the enthalpy of formation of CO2 and H2O gases. So we need to do, again, products minus reactants. So we're going to do 6 times our CO2 value. So 6 times negative 393.5. I'm just going to leave off my units. And they're all in kilojoules per mole, so we'll do that at the end. Plus 3 times water's value, negative 285.8. Okay, so products minus reactants. So let's do minus. There's 1 mole of benzene, so 1 times 49. And remember, lone elements that are in their natural state are 0. I mean, if you really want to put 15 halves times 0, I mean, go for it, but you don't need to, because anything times 0 is going to be 0. So 49 plus 0, we can just leave it off. All right, so let's put in our math here. 6 times negative 393.5 plus 3 times negative 285.8. So that's my product sum minus our reactants. 1 times 49 is 49. So we should have a delta H for the reaction of negative 3267.4 kilojoules per mole. I'm going to put up a few more examples if you are interested. Feel free to work through them. If you feel like you've got this down pat, you can feel free to skip forward to the end of the lecture. But I'll put this up, and I encourage you to pause the video, work through it, and in a minute I will put up the next slide that has the answer on it so you can check your work. So hopefully you worked through this, given the enthalpy of formation of those compounds, and you got the answer of negative 2801 kilojoules. Let's try another. Oh, we worked through this one already. Oh, actually, no, it's a little bit different. All right, we want to find 1 mole of PCl3. And here's your choices. So I'm going to skip forward here. Here are your options. And let's check your answer. So you got negative 319.7. What's the value of the unknown delta H right here? No, just kidding. This one, unknown delta H question mark. How would I find that? Hopefully you got negative 56.6 just by subtracting. How about this one? Which equation below defines the standard molar enthalpy of the formation of methanol? Standard molar enthalpy. What's the definition? A lot of choices here. They all get to methanol. Hopefully you chose this one, because remember, if we think about ethanol, what makes it up? Carbon in solid state, hydrogen, gaseous hydrogen diatomic, oxygen, gaseous oxygen diatomic. This is not in element in its standard state. This is not element in a standard state. This is not element in a standard state. So, and to be individual. All right, what about another one here? See if you can work through this one. And hopefully you got the answer of. And here's your choices. And again, here's your answer. Let's do another one. Calculate the standard enthalpy of reaction for this process. Given this, I'll give you some choices, multiple choice questions here. So here's you need to pause and write it down. Here's your choices. And the answer is, let's see if you got the right answer, hopefully. I've got two more for you, two more. Here's, we want to find the enthalpy of vaporization, so going from liquid to gas, given two reactions, two elementary reactions to get to our net target equation. See if you can figure that out. Here's your choices. And the answer is, and finally, see if you can find the standard molar enthalpy of formation using these target equations. And checking your work. Here's your answer. So that takes us to our very last section here, where we're going to see, do we have reactant or product favored reactions? So we've done a lot of thermodynamic practice in this section. The first two questions that we address, like how do we measure and calculate the energy changes associated with physical changes in chemical reactions? What is the relationship between energy changes, heat, and work? We addressed in this chapter, but the other two questions that we wanted to look at in this section, like how do we determine whether a chemical reaction is product favored or reactant favored at equilibrium? How can we determine whether a chemical reaction or physical process will occur spontaneously, that is, without outside intervention? Those we still have, and we're going to look more into that in chapter 18. We can, however, set the stage for consideration of these issues. So back in previous chapters, we learned that chemical reactions proceed toward equilibrium, and spontaneous changes occur in a way that allows a system to approach equilibrium. So reactions in which reactants are largely converted to products when equilibrium is reached are said to be product favored at equilibrium. Reactions in which only small amounts of products are present are called reactant favored at equilibrium. Now, in most cases, product favored reactions have negative values of delta H for the reactions. And reactant favored reactions have positive values of delta H for the reactions, but that's not always true. There are some exceptions. And so this will be covered more when we get to thermodynamics, actually in later chapters, and really more in Gen Chem 2. So this sums up our chapter 5, looking at enthalpy, chemical reactivity of energy and chemical reactions, and hopefully you have a really good concept and grasp on this. Again, there's always going to be extra practice problems for you to explore if you are interested.